Hello again. This is a relatively short session where we go through vertical plane flow simulations in Anaqsim. And it's a handy feature. It's not explicitly a separate kind of input or anything. You make use of confined domains and set them with a unit thickness, and it works quite well. I will go through several examples of vertical plane flow models and also discuss free surfaces at the end. So far in demonstrating Anaqsim, we've always had the domains in the horizontal plane. So the x, y coordinate system is in the horizontal plane and z would be vertical, normal to that. For vertical plane flow, we turn that domain on its end so that the y direction is vertical, the x direction is horizontal, and the z direction is normal to that vertical slice that we've created. In our equations, our general equations for flow, they're very similar to what we had before, except that we are looking at a unit thick slice of the aquifer. So our prism here is actually a little cube with a 1 unit dimension in the z direction, and our discharges in the domain are proportional to k, no longer T for transmissivity. Now we're looking at hydraulic conductivity because our thickness is 1. So K and T turns out are identical in this mode. So our general equation is written very similarly, except for a couple of things. We're using K and not T, and on the right-hand side, we no longer have those leakage terms for leakage out the top and bottom of our domain, which in the normal mode would be upwards and downwards to layers above and below. But in this mode, where it's turned on the side, there is no vertical, no leakage normal to the plane of the domain. We're assuming that the flow system we're modeling is two-dimensional in the vertical plane. There is no component in the z direction. So we can cut out the L sub t and L sub b terms from what had been our general equation, and we end up with this. One other change is that this term here is specific storage, no longer storativity or specific yield, because we're dealing with a confined situation where the water table position doesn't affect saturated thickness, and a unit thickness, so storativity is essentially specific storage here. When we combine these top two equations, we get this one, which is somewhat familiar, except that the right-hand side has fewer terms. It lacks those leakage normal to the plane terms. And in vertical plane mode, we can use the same coordinate transformation to achieve general anisotropy characteristics in our models, and basically look at these equations over here as though it's an isotropic situation, or we're dealing with the equivalent isotropic coordinate system and hydraulic conductivity after performing that transformation. We can use Anaqsim to simulate vertical plane flow, and we do that by just simulating a single level in a model and using only confined domains. We can still have heterogeneity, but all the domains need to be confined, and all of them need to be 1 unit thick in the plane, in the direction normal to the plane of the domain. So you do that by setting for your confined domain a top elevation 1 unit larger than the bottom elevation, and do that in every domain. And you can create your boundaries in an XY plane where X is horizontal and Y is vertical. I suppose you could reverse those. I always do it this way by default. You can have drains, and those will be modeled with well elements, and their discharges, like all the discharges in the model, are going to be discharges per unit width in the z direction, or the direction normal to the plane of the vertical plane flow model. Area sinks will only be used in transient models to simulate storage fluxes. There's no other purpose for them, since there is no leakage normal to the plane like you could have in a typical multi-layer model that's with the domains horizontal. The K3 values are still input with the domain input, but they aren't used, and they're irrelevant because there is no vertical, or not vertical, I keep saying that, no leakage or flow normal to this plane. And as I said before, for the storativity, use the specific storage, because our unit thickness is just 1, so even if we did call it storativity, it would be the same as specific storage. Let's walk through a few examples. This first one is a situation with an impermeable dam and flow under that dam from a higher head on the upstream reservoir side to a lower head on the downstream or tailwater side. So let me run through the boundaries in this model. This is the reservoir side, and this boundary is a constant head boundary all the way up to here. That's the bottom of the reservoir. This boundary is the bottom of the impermeable, say, concrete dam. Okay, so that's a normal flux specified boundary with a specified normal flux of 0. This boundary here is a head specified boundary at the elevation of the tailwater, which is lower than the reservoir. So it drives flow under this dam. This boundary here is kind of set far off to the right and impermeable, because it really doesn't matter much. There isn't much flow going on that far out. This is the impermeable base to our aquifer underneath the dam, and it's irregular. And again, we have an impermeable boundary down this left-hand side, because we're getting far enough away that there's not much impact about where that boundary is. So in this case, the hydraulic conductivities are isotropic. K in the one direction or x direction is the same as in the y direction. And because of that, we've got head contours in blue that are perpendicular to our red path lines, like you'd expect for isotropic. We do have heterogeneity. We've got this lens in the middle here, which is maybe a silt lens within sand or something. It has a conductivity that's 1/10 of the surrounding materials, and flow diverts around it to some degree, and not a whole lot crosses it. This second example is like the first, except that we have anisotropy now. We have an 8-to-1 ratio of the x direction conductivity to the y direction conductivity. And we get a very different looking flow net and flow system. And notice that the head contours with anisotropy are not normal to the flow path lines. And the flow tends to want to go horizontally more so than it wants to go vertically because of this anisotropy. But the same boundaries here: reservoir, constant head, impermeable under the dam, tailwater, constant head, and then impermeable base and left and right margins. This third example is like the second one, except that instead of the dam being impermeable and concrete, say, it is an embankment that has some conductivity, but a substantially lower conductivity than the underlying sand. And there's some new boundaries in here. The constant head boundary for the bottom of the reservoir is here, and then there's another stretch of constant head boundary running up the upstream slope of the embankment where it's saturated, and that's set at the same head as it is out here because the reservoir is continuous. We have this surface here, which is the water table surface or the free surface, and along that the head has to equal elevation, which it does. And in this case, I've said that there's no appreciable recharge coming through that, so it's set to a 0 normal flux along that boundary. And then there's an interdomain boundary here that separates the embankment from the underlying more permeable sands. The sands and then this siltier lens that's less conductive still have the 8:1 horizontal to vertical conductivity ratio, but the embankment itself, having been placed and manufactured essentially, is assumed isotropic. So the trickiest part of this is figuring out the free surface position correctly, and the condition that needs to occur along that is that the head needs to equal the elevation. So it's important when you do a vertical plane model with a free surface or water table in it that you use the actual elevations so you can easily check. So what you do to create this is you take a first guess at where this boundary is and then run the model and look at the heads along that boundary. For example, where 3.1 comes in and intersects that boundary, ideally would be at an elevation of 3.1. If it's at a lower elevation, then you need to move this boundary up higher. And you can easily do that in Anaqsim by roving your cursor around and checking heads. And then when you want to adjust this boundary, you click on it and you can graphically drag the vertices and nudge it up or down or what have you. So it's an iterative process to get that right. And this model took me maybe half hour to an hour to play with that boundary to get it right, or very close to perfect. And that gives me a real nice approximation. Remember, this is just simulating the saturated zone. So this is the saturated part of the embankment. The embankment would continue on and go up higher and then come back down, something like this. And the upper part here would be unsaturated, and we're not simulating that part of the system. We're neglecting any flow there. We're just simulating the saturated zone here. Let's look at some of the possibilities for free surface boundary conditions. When we have a water table, the head has to equal the elevation because it's atmospheric pressure there. And the water table itself is typically going to be modeled with a normal flux specified line boundary. And if you want 0 recharge, you can set it to 0. If you want some non-zero finite recharge, you can set that recharge rate, which would be the flux normal to this boundary. So you'd have to take into account the slope of it to some degree to estimate that rate to get it right. So the left-hand picture here shows a water table that is impermeable, no recharge coming in the top. It's also a streamline. The one in the middle here is a water table boundary. Again, the heads are equal to elevation in both cases, but in this case, the water table is a source of water because there's recharge. So you would have a finite specified normal flux along that boundary. The other possibility is a seepage face, and that might occur at the toe of an embankment dam, something like that. And again, the head has to equal elevation, but in this case, you would use a head specified line boundary because you know the geometry of that seepage face. Ideally, you could survey it and get the slope and so on. So you put in a seepage face, and usually that will transition to a water table at some point if you go high enough up the toe of the embankment or what have you. And you will have to have a junction between the seepage face, head specified line boundary, and the water table normal flux specified line boundary. And again, you would iterate, taking a first guess at where that is and a first guess at the water table configuration, run the model, and see what needs to be adjusted. Maybe that junction between the seepage face and water table needs to move a little higher or a little bit lower down the slope. And you can do that manually